This is our physics final project. My name is Cole.
My name's Anthony.
And my name is Rahul.
Kinetic energy is the energy of an object in motion. For example, on the Lido deck, a player is playing shuffleboarding. He hits the puck, and the puck gains a velocity of 3.5 meters per second. The puck weighs 0.357 kilograms. Now we can solve for the kinetic energy. So we have the given information. K equals half mv squared is the equation to solve for kinetic energy. We plug in the numbers, we get 2.1866625 joules. The correct sig figs is 2 because of 3.5 meters per second, and it is 2.2 joules.
Gravitational potential energy is the energy stored in an object due to its height. On the main deck, a man is climbing up a rock wall. He is 4.5 meters up the 7.5 meter rock wall. We can see here that he has a given mass of 80.7 kilograms. He is 4.5 meters up the wall, and the wall is 7.5 meters. Well, we can solve for GPE given that the acceleration of gravity is 9.8 meters per second, his mass is 80.7 kilograms, and that he's 4.5 meters up the rock wall, giving us a correct answer of 3,600 joules, incorrect sig figs.
Elastic potential energy is the amount of energy stored in an object as a result of it being stretched. For example, on the main deck, a 75 kilogram man is bungee jumping. He stretches the bungee cord by 22 meters. The bungee cord is located 25 meters above the ground. The problem is, how can we calculate the elastic potential energy of the bungee cord? To do so, we can use the equation for elastic potential energy, which is 1/2 times the spring constant times the displacement squared. Through researching on the internet, we found out that the spring constant of the average bungee cord is 15.2 newtons per meter. Plugging this into the equation and using the correct number of sig figs, which is 2, we get an answer of 3,700 joules.
Radiant energy is the energy given off by electromagnetic radiation. For example, on the Lido deck, there are tanning beds. These tanning beds give off ultraviolet rays. Ultraviolet rays have a frequency of 10 to the 14th hertz. Now let's solve for radiant energy. So we can see Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. The equation for radiant energy is equal to HF. We plug in the numbers, we get 6.63 times 10 to the negative 20th joules.
The law of conservation of energy states that energy can neither be created nor destroyed. However, in cases involving energy transfer, it can seem that energy was lost during the process. This energy loss can often be explained by various factors. To demonstrate this, we look back to the problem of bungee jumping on the main deck. So first we want to calculate the gravitational potential energy of the man. We know that his mass is 75 kilograms and that the initial height of the bungee cord is 25 meters. We can plug this into the equation GPE is equal to mgh to get an approximate GPE of 18,375 joules. Now, to calculate the energy lost during the transfer, we want to subtract the elastic potential energy from the gravitational potential energy, because in the ideal world, these two would be equal. So the energy lost with the correct number of sig figs comes out to approximately 15,000 joules. So although it may seem that a lot of energy was lost, it may have happened due to factors such as thermal, friction, and sound energy, factors which we cannot see with our own eyes.
Work is force being done to a moving object. Going back to the main deck problem, we are going to use the bungee again to solve work, but this time we are going to be using the givens they gave us in the problem of 75.7 newtons moving the bungee cord of a distance of 8.3 meters. We are going to solve a proportion to use our previous distance of 22 meters like this, giving us a Newton force of 200.65 newtons. We will apply this to our work equation, given our already distance of 22 meters and our new force, to get 4414 joules, converted into a correct sig fig of 4,400 joules.
Is when an electromagnetic wave travels through a new medium and changes direction. This new direction can be determined using Snell's law. For example, on the Machuca deck, there is a window made out of crown glass. Light traveling through the air hits the crown glass. What is the angle of refraction in the crown glass after light hits it? Using Snell's law, which is n1 times sine of theta 1 is equal to n2 times sine of theta 2, and we plug in all the numbers, and the only thing is left is sine of theta 2, we discovered that the angle of refraction once it enters the glass is 34.7. Just to show that light will exit how it entered because the two sides are parallel, we entered it in again and got 60 degrees, as we should.
Wave speed is defined as the frequency of a wave multiplied by its wavelength. On the Machuca deck, there's a treasure game going on in which there are a lot of cell phone signals. The cell phone signals are radio waves which have a frequency of 10 to the 6 hertz. Furthermore, the cell phone signals each have wavelengths of approximately 88.889 meters. So how can we calculate the speed of this wave? So to do so, we can use the formula v is equal to lambda times frequency. We can plug in the numbers given in the problem, which is 88.889 times 10 to the 6th. And using correct scientific notation, we get the speed of the wave being 8.889 times 10 to the 7th meters per second.
A mechanical wave is defined as a wave that requires to go through a medium. An example of this is the Machuca deck, where people are playing a ping pong game. When the ball is passed from player to player, there is a sound that's made. A sound wave is an example of a mechanical wave because you're required to go through a medium. This is an image we illustrated to demonstrate this. Electromagnetic wave is a wave that requires no medium to travel through. An example of this is the sun radiating waves upon the cruise ship as it is going through space to the Earth's atmosphere, requiring no medium to travel through whatsoever.
Diffraction is when waves bend and spread out to fill a space. For example, on the Nilo deck, if someone yells in one room, the sound waves will travel through the room and through an air vent into another room. As seen in this picture right here.
Wave interference is defined as when two waves combine to create a wave superposition. We can define this with the Neelam deck when two people belly flop into the pool, creating waves. We illustrated this through this image of these two people diving into the pool, having these two waves combining to make a much deeper wave at the point in which they collide.
A simple harmonic motion is a type of motion where the restoring force is directly proportional to the displacement of the object. One such example of this is on the Neelam deck, where we have a person who's getting ready to dive off a diving board. Here's an example of this situation. So a person who is getting ready to dive would jump up and down on the diving board, and this would set the diving board off in simple harmonic motion. Specifically, it would be bouncing up and down, trying to get back to its equilibrium, which is this position in the center right here. And the restoring force in our situation would be gravity.